Sulfur, represented in chemistry by the symbol S, is a solid yellow-colored mineral, one of the few elements found in a pure state in nature. It is tasteless and odorless. Sulfur is tremendously important to our daily lives. An automobile, for example, contains about 35 pounds of this vital element, not counting that used to manufacture the gasoline in the tank. Without sulfur, the rubber in the tires would be soft and gummy when hot, hard and brittle when cold. Huge quantities of sulfur are used in manufacturing virtually every part of the car. The battery is cased in rubber, hardened with the aid of sulfur, and the fluid inside is sulfuric acid. Sulfur plays a vital part not only in automobiles, but in nearly everything else we use, eat, or wear. Man has known and used sulfur since ancient times. Sulfur from volcanoes of the Mediterranean region was used by the Greeks and the Romans as a medicine to clean wool and to make torches. Until the early part of the present century, the volcanic isle of Sicily produced nearly all the world's supply of sulfur. In 1901, Hermann Frosch perfected a method of mining underground deposits found in the southern United States, and today, Texas and Louisiana produce 99% of the sulfur we use every year, plus a large amount for export. Derricks similar to those used on oil wells mark the location of the shafts leading to deposits of the yellow mineral 700 feet or more below the surface. Under the Frosch process, very hot water and steam, superheated to 170 degrees centigrade, is forced down to the sulfur beds. This melts the sulfur, and a stream of hot coming down through another pipe forces the frothy mixture of sulfur, hot water, and air to the surface. The water evaporates, and the sulfur solidifies into huge blocks, often weighing more than 1,000,000 tons. It is blasted apart. Loaded onto freight cars, and is shipped to the markets of the world. Sulfur has a number of interesting properties. It melts at a comparatively low temperature, about 115 degrees centigrade. As it melts, it turns to a brown liquid, becoming darker as the temperature is increased. At one point, it reaches a viscous state, but quickly turns back to a liquid as it approaches its boiling point of approximately 444 degrees centigrade. Like oxygen, sulfur has several allotropic forms. In the laboratory, we can prepare the 3 allotropic forms of sulfur: rhombic, monoclinic or prismatic, and amorphous or plastic. We can easily see that sulfur is insoluble in water. But it dissolves readily in carbon disulfide. If this solution is allowed to evaporate, crystals of rhombic sulfur will be formed. These crystals are octahedral, or 8-sided in shape. Sulfur in its natural state is in rhombic form, but the crystals are much smaller and often broken. If we heat sulfur to its melting point, about 115 degrees centigrade, pour it onto a filter paper and allow it to cool, needle-like crystals of monoclinic or prismatic sulfur will be formed. When monoclinic sulfur is cooled below 96 degrees centigrade, it slowly returns to rhombic crystals. To prepare amorphous or plastic sulfur, it is heated to its boiling point, about 444 degrees centigrade, and poured into cold water. Under these conditions, sulfur will not crystallize at all. but turn into a rubbery plastic state. Amorphous sulfur will also go back to rhombic form after a while. Thus, it can be seen that rhombic crystals is the only stable form of sulfur. The simplest compound of sulfur may be produced by burning it in air. As the sulfur burns or oxidizes, each sulfur atom combines with 2 atoms of oxygen from the air to form a gas, sulfur dioxide, SO2. Sulfur dioxide has a suffocating, choking odor. Sulfur dioxide has a number of commercial uses. It is used principally as a bleaching agent. Let's see what happens to this red geranium. If sulfur is burned in a furnace, sulfur dioxide is formed. If this gas is mixed with a plentiful supply of air and passed over a catalytic agent, such as finely divided platinum, each molecule is combined with an atom of oxygen from the air to produce a new compound, sulfur trioxide, SO3. If this compound is dissolved in water, hydrogen and oxygen atoms from the water are added to the equation to produce H2SO4, which is sulfuric acid. The manufacture of sulfuric acid is by far the greatest single use for sulfur. Actually, the process of making sulfuric acid commercially is much more complicated than the diagram we have just seen, although the basic principle is the same. Huge quantities of sulfur are required to manufacture the more than 8 million tons of sulfuric acid used in the United States every year. Power machinery is used to carry the yellow mineral to giant furnaces, where the sulfur dioxide is produced. After going through a complex system of tanks and coolers, the acid emerges in such great quantities that tank cars are used to ship it away. Sulfur is also used in the vulcanizing of rubber. Stretchy rubber articles such as hot water bottles and ice bags contain small quantities of sulfur. More sulfur is used in hard rubber, of which this cap is made. Sulfur, when mixed with such chemicals as lead arsenate, makes an excellent fungicide for preventing the growth of blights or mildew on plants. Sulfuric acid has literally thousands of uses. Here it is used to treat metals before they are tinned or galvanized. In this process, known as pickling, the metal is lowered into a turbulent bath of dilute sulfuric acid, where surface deposits and scale are removed by chemical action. One of the most important uses of sulfuric acid is in the manufacture of superphosphate fertilizer, of which tremendous quantity is used every year. In making this fertilizer, sulfuric acid is used on insoluble phosphate to convert it into calcium acid phosphate, which is soluble and therefore available as a plant food. Phosphate found in bones is converted into fertilizer in the same manner. In sulfur drugs, medical science has used the yellow mineral to forge a powerful weapon against disease and infection. Throughout the centuries, man has continually found more uses for sulfur, and the future may uncover many new sulfur compounds which will be of further benefit to mankind.